Well, of course, last time we did the inverse of a matrix, computing the inverse of a matrix, and so naturally the check-in has to do with that. It asked me to find the inverse of those pair of 3 by 3 matrices, and it says if it exists. So there's, you've been student for enough years to know that one of them is going to exist and the other one isn't. Let's see which one it is. Okay, let's get rid of that. There we go. All right, here's the paper. So let's see. The first one is 1, 3, 3, 1, 4, 3, and 1, 3, 4. Okay, and the method that we learned last time is to do Gauss-Jordan on this matrix, that is to reduce it to the identity matrix, to do Gauss-Jordan on this matrix while at the same time performing the same operations starting with the identity. So here we go. 1, 3, 3, 1, 4, 3, 1, 3, 4. And you put a vertical bar, like an augmented matrix vertical bar, 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. Now, so often in the past videos, I've been saying, I'll just show you the steps and you can fill them in yourself. But because this is a little bit different, I'm going to do at least a couple of steps. So the first one is minus row 1 plus row 2. And it goes 1, 3, 3, 1, 0, 0. And then the row that's changed goes 0, 1, 0. And then minus 1, 1, 0. And the third row isn't even mentioned. 1, 3, 4, 0, 0, 1. So I'm performing the regular Gauss's method steps. I'm carrying those operations over into this second half. Just, of course, we saw the theory, the reason why this particular operation does indeed produce the inverse. But one thing you can think, one intuition that can help to build your idea of what's happening here, is that this minus 1 down here in the row 2, column 1 position, in some sense remembers this operation. Okay, anyway, enough hand waving. So now I will take a minus row 1, add to row 3. And that gives me the 1, 3, 3, 1, 0, 0. 0, 1, 0, minus 1, 1, 0. Those, of course, are the unchanged rows. And then 0, 0, 1, and minus 1. 0, 1, and again, that minus 1 in some way remembers this operation is an intuition that a person can have. Ordinarily, in the Gauss-Jordan reduction, the next thing you do is to turn the diagonal entries into 1s. They happen to already be 1s. They don't happen to be 1s. I made up a problem so that they're 1s. And so now I turn and start pivoting up. The thing to remember about pivoting up is that it's easiest if you do it instead of from left to right, as I've been proceeding so far. It's easy if you do it from right to left. So use the 1 to get rid of the 3 kind of stuff. Here we go. So that's what minus 3 row 3, minus 3 row 3 plus row 1. It gives me 1, 3, 0 for that top of the left-hand side. 4, 0, minus 3. And then 0, 1, 0. Minus 1, 1, 0. And then 0, 0, 1. Minus 1, 0, 1. And then finally, all I have to do is use this 1 to get rid of that 3. So I take minus 3 row 2 plus row 1. And then I'll be done. I just have to say, let's see, it's 1, 0, 0, and then 7, minus 3, minus 3, right? Because minus 3 row 2 makes this a minus 1. You add to the 4, that explains the 7 kind of stuff. Then 0, 1, 0, minus 1, 1, 0, and then finally 0, 0, 1. Minus 1, 0, 1. Minus 1, 0, 1. And so the answer is that, A inverse is what's over here. 7 minus 3 minus 3. Minus 1, 1, 0. Minus 1, 0, 1. Okay? And you could try multiplying those two together and make sure, either way, either from the left or from the right, multiply it by this, and make sure that you get an identity matrix, which, given my arithmetic skills, is probably a good idea. But I'm not gonna do it. I'm just gonna forge ahead. For number 2, let's see. It is what 2, 2, 3, 2, 2, 3, 1 minus 2 minus 3, and then 4 minus 2 minus 3. And same thing, you put the 1, 0, 0, 0, 1, 0, 0, 0, 1. And you start in. So you take a minus 1/2, row 1 plus row 2. And also at the same time, I'm going to do minus 2, row 1 plus row 3. I don't know why I didn't combine those two, other than just wanting to illustrate a little more slowly. So 2, 2, 3, 1, 0, 0. And then I get 0 minus 3 minus 9/2. Can you see it says minus 9/2? Minus 1/2. 1, 0. And then 0, minus 6, minus 9, and minus 2, 0, 1. And now we've done so many Gauss's methods that I wonder if a person doesn't have some idea what's happening here, and spot, because your antenna is up, spot that the second row here is in the left-hand side of the matrix. The second row is the third row is twice the second. But plunging ahead as though I haven't noticed that. Minus 2, row 2, plus row 3, and I get 2, 2, 3, 1, 0, 0, 0 minus 3 minus 9/2, minus 1/2, 1, 0, and then 0, 0, 0. And I could stop because I know there isn't going to be an inverse, but I'll just go ahead just for the sake of having done it. Minus 2, 1. So minus 1, minus 2, 1. And here, because the matrix is singular, it has no inverse. Okay, so because I got a row of zeros, no inverse. So either you plunge ahead and you do Gauss-Jordan reduction and it goes the whole way through and you get an inverse, or else when you do Gauss-Jordan reduction you run into some snag, and that's the no inverse case. And those are two things that can happen. You either have a problem or you don't have a problem. Okay, so we're ready for the next section that we're going to talk about. So we now have been working for some time with the ability to represent a vector with respect to a basis, and we have emphasized that somehow this representation is the computational aspect of an object. That I've used the analogy that if I take a trip somewhere, that the real thing is the trip, and the pieces of paper with numbers on them that I hand in to the accounting folks, that those are somehow not real. Those are somehow the not primary. Those are somehow the evidence of the trip, the computational aspect, the computational thing they use to compute the trip, but it isn't really the trip. So what I've got here is that if you give me, for example, a vector, I can represent it with respect to some basis B1, and I get a bunch of numbers. Or I can represent it with respect to some basis B2, and I get a bunch of numbers. So what I want to do here is, what's the relationship between the two bunches of numbers? Is bunches, is that plural bunches of numbers? Anyway, what's the relationship between the two number bunches, I guess? So given a vector, I'm going to fix a vector, and I'm going to vary the bases. How does the representation vary? So first is to observe that that if you take a vector 1, 2, 3, because I'm not a very imaginative person, and you represent it with respect to two different bases, then you get two different representations. So it's easy to compute an example. There's an example. You fix the base. You fix the vector and you change the bases. Why then you change the representations? The question is, if I tell you E3 and B, can you tell me how to convert from 1, 2, 3 to 0, 2, 1? Right? So here's the idea. We've been emphasizing, I've been talking for some time throughout the sort of the third chapter about how we're trying to view that the maps are primary, and the sort of matrices and everything are not foolish by any means, but secondary. Something's got to be primary, and we're putting the maps as primary. And what we're talking about today is a great example of that the maps give a meaning to what we're doing, in the way that just saying, well, here, set up this linear system and then do Gauss's method on it, does not give a meaning. When I took this course, the way it was laid out, everything was set up a linear system, do Gauss's method on it, and you'll get the answer. And I left the course feeling that I could get all the right answers. I got an A in the course, but that I had never had any idea what was happening. I never had any kind of conceptual, here's the idea type of thing. So we're very focused on what the idea is here. We do a lot of computation, but we're very focused always on what's the idea behind the computation. That's where the sort of taking maps as primary pays off. Today is a great example. I want to translate from the representation with respect to B of a vector V to the representation with respect to D of a vector V. V is not changing. It's V here and it's V here. So I'm thinking of the identity map from V to V. The identity map from V to V. And so as I'm thinking of this picture, I wrote it up and down because ordinarily the map pictures go side to side, but I wrote it up and down because in the next subsection there's going to be another drawing where it's convenient to have it up and down. There'll be other things side to side, so that's why it's up and down. So I have a space. I'm mapping the vector V to itself, and I'm worried about what's the conversion. If you have a representation with respect to B and a representation with respect to D, how do you get from here to here? And of course we've seen how to represent a map. It happens to be this map, but so what? It's a map. We've seen how to represent a map with respect to the input and output bases, the domain and codomain bases. All right, so that's what I need. Change of basis matrix is the representation with respect to B comma D of the identity map. That's all. The fact that we take the maps as primary, that we look to the maps for the meaning of what we're doing, tells us that there's no tough computation involved here. You just simply write down the representation with respect to B comma D of the identity matrix. Excuse me, of the identity map. That's all. So I wrote exactly what that matrix is, but we know what that matrix is. So you figure out here what is the identity map acting on the first basis vector, what is the identity map acting on the second basis vector, etc., all the way down to the identity map acting on the nth basis vector. And then you represent the result with respect to D, the result with respect to D, the result with respect to D, the result with respect to D. Of course, the identity map acts on beta 1 by setting it to beta 1. That's what the identity map does not much. All the way out to it maps the last basis vector to itself. And then we just represent those folks with respect to the codomains basis, the output basis, right down here, the D. All right, so of course we're going to compute a couple of those, but my point about the whole map versus matrix thing is that because we're taking the point of view that we want these things to have a meaning, we want to think of them in terms of maps, that the meaning is clear. There's no linear system to set up. The meaning is clear. Okay. So that gives me this. Is that if you have a representation with respect to a basis B, and you want to convert it to a representation of the same vector with respect to a basis D, why you want to left multiply by the matrix, representing the identity map with respect to B comma D. Okay, and the converse works also. If you have a left multiplication by a matrix that changes bases, then M is a change of basis matrix. And the book has the proof. I want to do the computations because we take that a person is watching the videos first, then reading the book, and then doing the homework. Okay. So you know how I work. I'm going to write down some not too hard but not too easy cases, and then I'm going to do the computation. Because I think by taking out a pencil and saying to yourself, what goes here? And then looking up at the example when you get stuck, that's how a person makes progress. We zigzag our way to knowing the truth. First you start out knowing 70%, then 85%, then 95%. So here we are, we're hoping to make a first cut at it. Okay, so I have the domain space is P2. I'm going to change representations from with respect to B to with respect to D. So I've got to compute the representation with respect to B comma D of the identity map. Okay, so what does the identity map do to the first of capital B's basis vector? What does the identity map do to the second of capital B's basis vectors? What does the identity map do to the third of capital B's basis vector? And of course the identity map doesn't do anything at all. So that's the outcome of applying the identity map to the basis vector 1. That's the outcome of applying the identity map to the basis vector 1 plus x. That's the outcome of applying the identity map to the basis vector 1 plus x squared. Represent those with respect to D, represent with respect to D, represent with respect to D. And D is simple enough that a person can eyeball the answer. In any event, I'll spare you the agony if eyeballing fails you for one of the three. It turns out when you do the arithmetic that the representation with respect to D of the first basis vector in capital B is this. The representation with respect to D of the second basis vector in capital B is this. The representation with respect to D of the third basis vector in capital B is this. And we know how to make the representation of the map as a whole. You write those three vectors in order. That's why we have bases coming in order. Write those three vectors in order. There they are, and it makes a matrix. And of course, I did an example. Suppose that you have a vector that is v minus x plus 3x squared. You can calculate here that the representation of that vector with respect to b is this. And you can calculate that the representation of that vector with respect to d is this. It's of course very easy to go from the representation to the vector. You just take 3 times the first minus 4 times the second plus 3 times the third and just check. Likewise 1/2 times the first, 1 minus 1 times the second, and 5/2 times the third, and just check that it works out to be 2 minus x plus 3x squared. And a person can easily check that if you take this matrix and you multiply it by 3 minus 4, 3, here's the 3 minus 4, 3. Multiply it by 3 minus 4, 3, you do indeed get 1/2 minus 1 5/2. So the diagram that we had, this diagram right here, it does exactly what it's supposed to do. It changes the representation with respect to B to a representation with respect to D. Okay. The next result is that a matrix changes bases if and only if it's non-singular, and only if it's an isomorphism. A matrix changes bases if and only if it's non-singular, and as often happens, we're going to do an example rather than the proof in these slides. Just that's the way we operate, trying to get an understanding, and the understanding leads to a proof, and then that bundle taken together leads to the homework. So here's an example. So I'm going to take a non-singular matrix M, and any non-singular matrix M decomposes into a product of elementary reduction matrices, right? So we can show that M changes bases by showing that each Ri changes bases, right? So you remember that you Gauss-Jordan reduce M to the identity, and then you express that as identity times all of those. And so we can show that M changes bases by showing that each Ri changes bases. Now, I'm not going to show the proof shows that each Ri changes bases, but here's an example. I took minus 4 row 1 plus row 3. I took that matrix, the matrix that performs minus 4 row 1 plus row 3, and I multiplied it by the representation with respect to B of V, and I don't have that. I just have R1, R2, R3. It's a 3 tall vector with letters there, and I did the matrix vector multiplication, and of course what you get is R1, R2, and then it does indeed take minus 4 row 1 plus row 3. Row 1 is pretty simple, but anyway, it does it. It takes minus 4 row 1 plus row 3. If this is the representation with respect to capital B, and this is capital B, then the right side is the representation with respect to this B hat. So if if this represents a vector v with respect to capital B, then this represents the vector v with respect to this b hat, because look, R1 times beta 1 plus 4 beta 3, that's the first thing here. R2 times beta 2, that's the second thing here. R3 times, minus 4 R1 plus R3 times beta 3, and when you add it all up, it adds up to what it's supposed to add up to. Verifying that b hat is a basis is routine, that's what the proof has to worry about. But verifying that b hat is a basis is routine. That if b is a basis, then b hat is a basis. So that's routine. Checking that it's linearly independent and that it spans the space is routine. Okay, so that is to say a matrix is non-singular if and only if it represents the identity map with respect to some pair of bases. A matrix is a non-singular matrix. Remember the definition of non-singular matrix. Square, and when you do Gauss's method on it, you get to echelon form, no zero rows. So a matrix is non-singular if and only if it represents the identity map with respect to the appropriate pair of bases. Okay, when we come back next time, what we're going to want to do is to think about how we change not just the representation of a vector with respect to the input and output bases, but how do you change, if you have a matrix representing a map, what happens when you change the bases? So the map is represented with respect to some b comma d. What happens when you change the bases to some b hat comma d hat? How do you translate from the one to the other? Okay, very good. Bye-bye.